we will see few problems on finding the number of divisors, the sum of divisors and the product of divisors of n, and also amicable numbers, perfect numbers. Find the smallest number with the given number of divisors, and also find the number of numbers not divisible by certain primes in a given number. Now in the first problem we have three subdivisions. We want to find the number of divisors, sum of divisors and the product of divisors of these three numbers. So first we shall consider this 840. By the fundamental theorem on arithmetic, by performing this division, we can write out 840 as 2 cubed 3 into 5 into 7. So that part, using fundamental theorem on arithmetic, we are able to write 840 as this. Now using this formula, we can find the number of divisors. See here, this is of the form P power A, Q power B, R power C, S power D, like that. So you have the number of divisors to be A plus 1, B plus 1, C plus 1, D plus 1. Here A, B, C, D are 3, 1, 1, 1. So when we find the product, we get it as 32. Now the sum of divisors, we have the formula for that to be this. So here 2 cubed we have, so 2 to the power 3 plus 1 minus 1 by 2 minus 1, and here it is 3 power 1. So we make use of this, so we have 3 power 1 plus 1 minus 1 by 3 minus 1, and in the same way for 5 and 7. Now this, when we simplify, we get as 15, 4, 6 and 8. That on simplification gives you 2880. Now the product of divisors, using this formula, we have already found out the number of divisors, that is 32. So that 32 divided by 2, that gives us 16. So n to the power 16 will give the product of divisors. So in the same way, if this number is given 1458, then performing this division, we have this being written as 2 into 3 power 6. Then the number of divisors here, A is 1, so A plus 1 means 1 plus 1, and B is 6, so 6 plus 1 we have, and the product gives us 14. And again make use of this formula, sum of the divisors. So using that, we have only two numbers, so we have 2 to the power 1 plus 1 minus 1 divided by 2 minus 1, and this one 3 power 6 plus 1 minus 1 by 3 minus 1. This on simplification gives you 3279. And the product of divisors, we have sum of divisors, number of divisors to be 14. So that divided by 2, that gives us 7. The number is 1458. So this is the product of divisors. Now in the same way for 288. Okay, here we have considered 2 power, this is wrongly written, this is 288, this one is 288. So the number of divisors for this, again performing this, we have 2 to the power 5 into 3 square, so we have this, and the number of divisors is 5 plus 1 into 2 plus 1, so that gives us 18. And again using this formula for the sum of the divisors, we get this. And here we have 18, so 18 by 2, 9, so the number being 288. Here alone there is a mistake, 288 it should be, so we have 288 raised to 9. Next we have the definition of amicable numbers. Two numbers n and m are said to be amicable numbers if sum of divisors of n minus n is m. And the same way, if we subtract m from the sum of divisors of m and we get n, means these two numbers, these two together should hold good. Only then we can call n and m to be amicable numbers or friendly numbers. Now here we are trying to prove that 220 and 284 are amicable numbers. So for 220, first we find the sum of the divisors, that gives us 504. And for the other one, that is for 284 we find, and that gives us 504 again. But sum of the divisors of 220 minus 220 is 504 minus 220, that is 284. And here it is 504 minus 284, that gives us 220. So from 1 and 2 is what we have. That is, they satisfy the condition for them to be amicable numbers. So 220 and 284 are amicable numbers. So these we have to perform to write out the sum of the divisors. To use the formula, it has to be brought in the standard form. That is, using fundamental theorem on arithmetic, it has to be written, and then only all this are to be performed. Now we have the definition of perfect number. So we are asked to define a perfect number and give an example. So a number n is a perfect number if sum of divisors of n minus n is n itself. So we are having few examples: 6, 28, 496. These are all perfect numbers. So n, if we consider, it is if it is taken as 6, then it is 2 into 3. Sum of the divisors using the formula, if you find, we get it as 12. So sum of divisors of 6 minus 6, namely 12 minus 6, gives us 6. And therefore 6 is a perfect number. And the same way for sum 28. Sum of the divisors of 28 is 56. Subtracting 28 from that, we get 28. And 496 is another number. So for this also the division is to be performed, and write it in the form P par A Q par B, that is fundamental theorem arithmetic. So you make use of that and use the division method, and write 496 as this. So sum of the divisors is 992. Subtracting 496 from that, we get back 496. So these three are perfect numbers. Now we have this problem. Using this, we can find very many examples for perfect numbers. Now suppose we have 2 power n minus 1 to be a prime number, then we can have this to be a perfect number. 2 power n minus 1 multiplied by 2 power n minus 1 to be a perfect number. Now we are given this to be a prime number, so we shall take it as some p. So that is given to us, and n, this number you take it as n. Our aim is to show that this n is a perfect number. Now we can rewrite this as, because 2 power n minus 1 is taken as p, this one will be 2 power n minus 1 into p. Now using this formula, we can find the sum of the divisors of n, and that we get as, here it is n minus 1, so n minus 1 plus 1 minus 1 by 2 minus 1, and here p power 1 plus 1 minus 1 by p minus 1. So you get p square minus 1 by p minus 1. This can be written as p minus 1 into p plus 1. Cancelling p minus 1, we have p plus 1. And this is nothing but 2 power, this 1 and 1 will get cancelled, giving 2 power n minus 1, which is taken as p. So the whole lot, sum of divisors of n whole lot, becomes p into p plus 1. Also, since p is this, we have 2 power n to be p plus 1, and therefore 2 power n minus 1 will be p plus 1 by 2. Now n is 2 power n minus 1 into p, here we have written, and in terms of p, if you want to rewrite this, we have already just substitute, so you get this p into p plus 1 by 2. So sum of divisors of n minus n, sum of divisors of n already it is computed, so this is what we have, and this one n is nothing but this. Subtracting this from this is what we get, p into p plus 1 by 2, and that p into p plus 1 by 2 is nothing but n. So we have sum of divisors of n minus n to be n, and therefore n is a perfect number. So whenever this is a prime number only, this will be a perfect number. Now next is we find the number of divisors of 480 excluding 1 and 480. We have already found out the number of divisors of 480 already, or for 240 or whatever may be the number, but here excluding two numbers. So first we have to perform this and write out this as 2 power 5, 3 and 5. Then the number of divisors formula, use the formula, you get this. So if you want to exclude 1 and 480, then subtract 2 from that, so you get 22. Then this problem here, see, so far we have been finding the, given the number, we found out the number of divisors. So here number of divisors is given, and there can be lot of numbers with so many divisors. But here the question is, what is the smallest number with number of divisors? 14. So let the required number n be. So we write it in the form 2 power a, 3 power b, 5 power c, and so on. Then by the formula we have number of divisors to be a plus 1, b plus 1, c plus 1. So to find the smallest number whose number of divisors is 14, we write it not as 2 into 7 but as in the descending order, 7 into 2. Here we write in the ascending order, whereas here the indices, to compute them, we write the number of divisors in the descending order as product of primes. Not prime powers but product of primes. So we have this a plus 1, b plus 1, c plus 1, etc. equated to this 7 into 2 into 1 into 1. How many ever times we want, we can have. But anyhow, they will not contribute any value, because in that case, for corresponding to them, the indices will be 0. So it is enough we consider only these two. So a plus 1 equated to 7 and b plus 1 to 2 to get a as 6 and b as 1. So the smallest number with the number of divisors 14 will be replace a by 6 and b by 1. So that gives the relevant answer. So here what is to be noted is these are to be written in the ascending order, whereas number of divisors, they have to be written as product of prime numbers, not prime powers, only prime numbers, and that too in the descending order. We have one more example. Find the smallest number with the number of divisors 28. So we shall take the required number to be this. The number of divisors we know to be a plus 1 into b plus 1 into c plus 1. Now 28 is written as, you should not write it as 7 into 2 square, but it should be written as 7 into 2 into 2. Product of prime numbers, not as product of prime powers. So here only product of prime numbers, that is to be remembered. And in the previous case, we have to equate the corresponding terms. So we get a as 6, b as 1 and c as 1. So substituting the values for a, b, c is what we get. So there again, there can be any number of numbers with so many divisors. But what we have found here is the smallest one. So next is to find the number of numbers divisible by 2, 3, 5 in certain number. It can be even 7, whatever prime number that you have, you can include them, and for which this is the method that we adopt to find the number of numbers not divisible by certain primes in a given number. So here the number given is 100. Now we shall take a1 to be the set of all numbers divisible by 2 in 100, and we consider the integral part of this kind of method that we have already come across in finding our formula for phi of n. So the number of such numbers divisible by 2 is n by 2, because the prime number here is 2, so you have 100 by 2, and that is 50. And the same way, number of numbers divisible by 3, integral part only we consider, 100 by 3 we have, but only integral part that we consider. And in the same way for this one, 100 by 5. When we have the intersection, that is the numbers in n, this denotes the set of all numbers in n divisible by both 2 and 3, and here is taken as 100. So it will be again the integral part 100 by 6, that is 16, and then 3 and 5 means you have 100 by 15. So again integral part is taken, and this one 100 by 10, that is exactly 10. Now again a1 intersection a2 intersection a3, it is the set of all numbers in n divisible by 2, 3 and 5. So here this is not there. It is 100 by 2 into 3 into 5, that gives you 3. So you again integral part is considered, this is not there. So by inclusion exclusion principle, all these stories are known to us. So we find the sum of this, so that gives 103, and this one is 32 and this one is 3. So 74 numbers in from 1 to 100. There are 74 numbers which are divisible by 2, 3, 5. But our aim is to find the number of numbers not divisible by 2, 3, 5 in 100. So 100 minus this one will give the required answer. So the number of numbers not divisible by this 2, 3, 5, even 7 means you'll have to extend the concept. And if not 100, it can be 200, 300, 500, 1000, and etc. So for all of the problems, the same method is to be adopted. Thank you.